So we're going to start by looking at this reaction, and the objective of this video is simply to answer the question of how many moles of HNO3 or nitric acid are produced when we add 6 moles of NO2 and 4 moles of H2O. And I'm actually going to start by zeroing in on this and just labeling this. As you might predict, this is one reaction, and the way I'm going to write that is 1R X, and that is the lazy chemist way of writing reaction. And when you're looking at this, you see, of course, the reactants on the left and products on the right. And basically what this represents is an input and an output of the chemical reaction. And in even simpler terms, it's kind of like a recipe for running one chemical reaction. And so just like you are making a sandwich or a hamburger or a cake, it represents the ratio of what you should put in to get that desired output. And so if you really want to get down detailed about what the values that you see here represent, this 3 right here in front of the NO2 represents that it's going to take 3 moles of NO2 to run one reaction. And even though there's nothing here in front of this water, what that represents is that it's going to take 1 mole of H2O to run one reaction. And just in the same exact way, if we go over to the product side, this 2 represents that for every reaction that you run, you get out 2 mole HNO3. And this, there's no coefficient here, so we interpret that as 1 mole of NO that you get out of a reaction. And so I like to think of these coefficients as units, and it's really, really helpful to understand the sort of recipe for a chemical reaction. But let me just be very clear about how this analogy of thinking of it as a recipe can kind of be a little bit limited. So if we think about a cake and you think about, okay, maybe I add a little bit too much sugar, all that's going to do is make a sweeter cake, right? But if I added, say, in this particular chemical reaction, a little bit too much water to run a perfect ratio reaction, then all I'm going to end up with is water left over, water in excess. And so if we depart from this chemical reaction, we go actually up to the question that we're asking here. These values, the 6 moles of NO2 and the 4 moles of H2O, are incredibly important to quantify and understand, because those numbers that you actually put into the reaction system can literally be any positive number under the sun. They can be whatever you want. And so it's really important to be able to quantify what we would call the limiting reagent and the reagent in excess in order to figure out how much products are formed. And so that's going to be the objective here, is to solve this problem, but also understand the differences between the coefficients that you would see in this balanced chemical reaction and the values that you put in, which are kind of defined by the person doing the experiment and can be whatever you want. So reaction stoichiometry is all about quantifying how much products you get and maybe even how many reactants are left over with any given input by using that balanced chemical reaction. All right, so let's solve for this problem, which is how many moles of HNO3 are produced when we add the 6 moles of NO2 and the 4 moles of H2O. Now, this is a limiting reagent problem, and so the step that comes after balancing and looking at this reaction is going to be to find the limiting reagent. So I'm going to write that right here. Find the limiting reagent. I'm going to call that LR. And the way I'm going to do that is I'm going to figure out how many reactions I can run. Remember that this recipe that I have written here is one reaction. And so if I take the 6 moles of NO2 and I want to figure out how many reactions I can run, well, look at these units right here. It takes me 3 moles of NO2 to run one reaction. So that means with my 6 moles of NO2, I can run 2 reactions. So what about that water? Well, I have 4 moles of water. And then for every reaction, it's going to take me 1 mole of water. So for every reaction, it's going to take me 1 mole of water. And so maybe some of you are thinking, as we're working through this, all I'm doing is dividing by the coefficient of the balanced chemical reaction. And that would be a head-on perfect assessment of what we're doing. We are taking the number that we input into the chemical reaction, we're dividing it by the coefficient in the balanced chemical reaction. And so that's going to get me the ability to run 4 reactions. Well, the limiting reagent by definition is going to be the reactant that I can run the fewest number of reactions with. So the fact that I can run 2 reactions with the NO2 and 4 reactions with the water means that I can technically only run 2 reactions. So this is my limiting reagent, and this is in excess. And so this 4 really becomes irrelevant for the rest of the problem. This 2 reactions is the amount of reactions that I can actually run with the amount that I have. And so the last step here to get to my answer is find the amount of HNO3, which is really what the question is asking for. And so I know that I can run 2 reactions. And I know that for every reaction, I am outputting 2 moles of HNO3. Where did I get this 2? I got it right from the balanced chemical reaction. That for every reaction I run, I am getting out 2 moles of HNO3. And that's going to get me an answer when I do the math here of 4 moles of HNO3. And that is my answer. Now, the one thing I want to leave you with in this video is that even though this might seem like a straightforward problem, it never gets more difficult than this in terms of the theory. If you can understand this core idea right here, reaction stoichiometry will be manageable from this point into the most difficult problems of introductory chemistry.